I am going to start a new lesson, electromagnetic induction. Before the 18th century, people thought that electricity and magnetism as different unrelated topics in the field of physics. But in the 18th century, when Ørsted was teaching or demonstrating an experiment to his students in his classroom, he discovered that a current carrying conductor could produce magnetism or magnetic properties or magnetic behavior around it. So he discovered that a current carrying conductor could produce magnetic field around it. So he, along with Ampere, conducted a series of experiments to give proof to this. Okay, so after that, in the next century, that is in the 19th century, Faraday and Henry, they conducted series of experiments to discover the converse effect. That is, from magnetism, varying magnetism or varying magnetic field could produce electricity. This was the converse effect which was already discovered by Ørsted and Ampere. So Faraday and Henry, they discovered the converse effect of this. So imagine a world without electricity, without electric trains, without TV, without electronic gadgets, without cell phones. So the world would have been very horrible. It would have been very hard life for us. So, but fortunately, we have everything. We have TV, we have cell phones, modern day gadgets, everything we have. So modern day generators, transformers, everything is there. So all these, they are because of this electromagnetism. So varying magnetic field generates electric current, or electric current is generated by the varying magnetic field is known as electromagnetic induction. So electricity is induced here. Electricity is induced because of varying magnetic field. So that is known as electromagnetic induction. I'll repeat again. The phenomenon in which electric current is generated by varying magnetic field is called as electromagnetic induction. So these were the experiments that were conducted by Faraday and Ampere. So the first experiment was coil magnet experiment. So here we have a coil here, a copper coil, and which is connected to a galvanometer. So here we have a magnet, a bar magnet, which has north pole and south pole. So the galvanometer is used to detect small variable current. So this galvanometer shows deflection when a current is observed here, or when a current is present in this circuit. So what this Faraday did was, he brought this magnet close to this coil. As he brought this magnet close to the coil, he observed that the magnetic field was varying here, because a magnet will produce magnetic field around it. So there was a varying magnetic field here. Because of that varying magnetic field, this galvanometer showed a certain amount of deflection. Okay. Then again he took this magnet away from the coil, and again he observed the deflection in the galvanometer, but in the opposite direction. Okay, when the magnet was kept stationary, he didn't observe any kind of deflection in the galvanometer. But as he kept moving the magnet towards, when the magnet was kept stationary, he didn't observe any kind of deflection in the galvanometer. Since there was no varying in magnetic field, he could not observe any kind of deflection in the galvanometer. But as he brought this magnet close to the coil very fastly, he observed the motion in the galvanometer to go a faster way. Okay, it could move faster. So when he increased the speed of this magnet, which was coming closer to this coil, even the galvanometer reading or galvanometer deflection was also fast. So here he observed that the relative motion between could produce electric current and which was observed in the galvanometer. Okay, so the next experiment which was conducted by them was coil experiment. Here, one coil was kept stationary and the other coil was kept moving here. So here, one coil, that is C1, is connected to the galvanometer. Then here we have one more coil which is C2, which is connected to the battery here. So here, since it is connected to a battery, there will be a current that is flowing in this coil C2. So since the current is flowing through the coil C2, there will be magnetic field around it. So as the coil is brought close to this coil C1, when the coil C2 is brought very close to the coil C1, he observed a deflection in the galvanometer. When the same coil C2 was taken away from the coil C1, he observed the deflection but in the opposite direction. Okay, so when the coil C2 was kept stationary, he didn't observe any kind of deflection in the galvanometer. So he observed that the relative motion between the coil C1 and C2 could produce electric field in the next experiment. So the next experiment here we have, even here we have two coils here, C1 and C2 is here. C1 is connected to the galvanometer and the coil C2 is connected to the battery as well as a tapping key here. This is a tapping key, just like a switch. Okay, so as soon as this, here he didn't move any kind of coil here, but what he did was, he pressed the starting key here. As soon as he pressed the tapping key, he observed a deflection in the galvanometer. And then in the next step, he pressed and held the key here. So even after that, he didn't observe any kind of deflection in the galvanometer in the primary coil or the C1. So after some time, he released the key here. So as soon as he left the key or released the key here, he observed a deflection in the galvanometer. So this proved that there was a presence of electricity in the coil here. So these three experiments, after doing all these three experiments, he discovered and proved that there was a presence of electricity because of varying magnetic fields. I think this is magnetic flux. So magnetic flux is the number of magnetic field lines. So these are the magnetic field lines passing through a particular area which is held perpendicular to the flow. Which is held perpendicular to the flow is known as magnetic flux. So maybe if an flux is like this, which is held perpendicular like this, which is held perpendicular to the flow is known as magnetic flux. So the amount of magnetic field lines flowing through a particular area which is held perpendicular to the flow is known as magnetic flux. We need to know this magnetic flux. So the next one is, so next topic is Faraday's law of induction. So this is our next topic which is very important. So Faraday gave a law to this induction or electromagnetic induction. So it states that the magnitude of the induced EMF, the magnitude of the induced EMF is equal to the time rate of change of magnetic flux that is present in the circuit or coil. So I'll repeat again. So the magnitude of the induced EMF is E. This E is the induced EMF. So E is equal to, or the magnitude of the induced EMF is equal to time rate of change of magnetic flux. So rate of change of magnetic flux is equal to d phi b by dt. So only magnetic flux is phi b. So the magnitude of the induced EMF is equal to the time rate of change of magnetic flux that is present in the circuit or coil. So this is Faraday's law of induction. So here we have a negative symbol here. So this negative symbol says that the induced EMF and the current is opposite to the magnetic field. So the negative symbol indicates that the induced EMF and the current form is always opposite to the magnetic field here. Okay, so actually literally in the Faraday didn't give this negative symbol. He only gave E is equal to d phi b by dt. So for this Faraday's law, there comes one more person called as Lenz. So this person, Lenz, gave a correction to this Faraday's law. So he gave this negative symbol literally to this Faraday's law of induction. So this Lenz gave one more law to this addition to this. So it is called as Lenz's law. So this Lenz's law says that the polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. So here E is equal to minus d phi b by d. This was given by Lenz's law. Okay, it says that the polarity of the induced EMF is such that it produces a current that opposes the change in magnetic flux that created it. So this is what Lenz's law says. So for this Lenz's law, this Lenz gave a verification for this. So the next topic is verification of Lenz's law. So here, what he did was, he took a coil here. He took a coil and he brought a magnet, a bar magnet, close to this coil. Okay, so when the north pole of the bar magnet was brought close to this coil or the circuit, so he took the coil here. So when the bar magnet, when the north pole of the bar magnet was brought close to this coil, he observed that the flow of current was in anti-clockwise direction. Okay, since the current was flowing in anti-clockwise direction, the current was opposing this magnetic flux here, or the building magnetic field here. So the current was literally opposing this magnetic field or magnetic flux here. So when the north pole of the magnet was taken away from the coil, he observed that. So look here, this is the next scenario. When the north pole of the magnet was taken away from the coil, he observed that the current was flowing in clockwise direction here. So this is clockwise. Here, the current was flowing in anti-clockwise direction. So here, since the current was flowing in clockwise direction, there was the opposition to the flow of this magnetic flux here. So magnetic flux kept on reducing. So if you take a magnet away from the coil, literally the magnetic field decreases when you take it away from the coil. So here he observed here. So the north pole of the magnet was literally acting like a south pole of the magnet here in this case. So the current was opposing the magnetic field in this experiment. So for this opposition, he proposed that it required a person to move the magnet to and fro here. So for this movement, it was a mechanical kind of work there. So mechanical work was observed here, or the mechanical energy was given here. This mechanical energy was in turn converted into electrical energy. So this Lenz's law obeys law of conservation of energy here. So that is the significance of this Lenz's law. So the significance of Lenz's law is it obeys law of conservation of energy. Okay. So the next topic is derive the expression for motional EMF. So this is the next topic. Let us derive the expression for motional EMF here. So let us consider a conductor P, Q, R, S to be a conductor and PQ be the movable part of the conductor here. So PQRS is the conductor and it's a rectangular conductor here. Then PQ is the movable part which could be moved to and fro here. Then let X be the distance between PQ and RS and L be the length of the conductor here. Then B be the magnetic field here. Magnetic field. So PQRS is the conductor here. It's a rectangular conductor. PQ is the movable part of the conductor. Let V be the velocity of this movable part of the conductor PQ. Then L be the length of the conductor and X be the distance between PQ and RS here. Then, so let us take the area of this conductor here, A. So area is given by length into breadth. So length is L here. So the breadth is X here. So area is equal to L into X here. Then let us find the magnetic field here. So magnetic flux here. So the magnetic flux phi B is equal to, so we have an expression for this. It is BA cos theta, which is BA cos theta here. So magnetic field phi B is equal to B A. So A is Lx into cos theta here. So cos theta that is equal to, that is theta, the value of cos theta, the value is here 0. So cos theta, so cos 0 is 1 here. So phi B is equal to B L X. So into 1 is only BLX. So let us take the Faraday's law of induction here. According to Faraday's law of induction, E is equal to minus d phi B by dt here. So E is equal to minus, so d by dt into phi is B L X. Okay. Then E is equal to, so here B and L are constant here, only X is variable. So because when we move the conductor, PQ movable part of the conductor, only the distance between the PQ and RS is varying here. So when the conductor is here, the distance is less here. When it comes here, even it is more less. But when it is far coming away, then the distance is more here. Only X is varying here. So X is variable. Apart from that, the magnetic field B is constant already. The length of the conductor is also not varying here. Even L is constant here. So B and L, they are constant. So minus BL into dx by dt. Now, so this dx by dt, what it is? So dx by dt is equal to, so here the distance is reducing here. Distance between PQ and RS is reducing here. When we move the conductor here from here to here, the distance is reducing. So the P is the change in distance or the change in displacement here. So the rate of change of displacement is velocity here. So that is V. So it moves with the velocity V here. So that V we shall take care. But we shall have a negative symbol with this, because the negative symbol symbolizes that the conductor PQ, or the movable part of the conductor PQ, moves in the negative x-axis direction. So this is the negative x-axis. So I hope you know that this is x and even this is x, sorry, this is y. So this is negative x-axis and this is negative y-axis. So here the conductor is moving in this direction. So it is negative x-axis here. So definitely it is negative x-axis. So we have taken negative here. So now E is equal to minus BL into V. So negative will get cancelled. E is equal to BLV. So this is the expression for motional EMF of the conductor. So this is the expression for motional EMF. The name motional EMF comes because there is a movement of this conductor here because of motion. So because of motion itself, EMF is produced here. So that is because the conductor is moving to and fro here. So it was stagnant here. After that, we kept on moving this conductor. After that itself, we got the EMF here.